virtual machine design issues, concepts, protections, things we actually, we learn for, how to design the virtual memory and VM API with emphasis of, several, libc, malloc, free, libc API and BRK, SBRK, and most importantly, mmap. So VM APIs, we talk about that. Okay, so last time we talking about VM APIs. Then we are moving to address translation. Such as base and bound VLAN, base and bound, and segmentation, and paging. Then we start learning some, useful features using paging. We learn VM, some functionalities, such as sharing, copy and write using the paging, and swapping. The swapping is like how to managing the physical network. If you learn this stuff, that actually kind of conclude the lecture of the virtual memory section. So learn VM design first. We already talk about VM design and virtual machine APIs. And today we will learn address translation method, address translation mechanisms. And this is like one lecture. And paging and some kind of sharing is also, consists of one separate lecture. So learning the paging mechanisms in detail, and learn how to share pages, physical memories, and using the sharing and paging, how do we implement copy and write? For example, fork happens. What is kind of how to implement copy and write on paging? Okay, then physical memory management with emphasis on how to use it, how to swap physical memory to storage, which is like some mechanisms and policies about physical memory management. That is overall information you learn. So this is kind of 4 important big chunk. Okay, so you have to get understand. So in the virtual memory, I first introduced this design term of level of interaction. We call that, and so for protection, virtual memory, so we don't run processes in each different address space and map into physical memory. Okay, so the basic purpose of virtual memory is abstracting physical memory for protection. And so we learn some protection mechanism, right? So hardware-based protection mechanism when address space is legal, address space virtual address and virtual address is translate physical memory by hardware. Otherwise, it raises exception, pay default exception. We learn that, and therefore we looking over important virtual memory design goals: protection, transparent things that happens, but that does not expose to what happens underneath is not exposed to application, transparency and efficiency in terms of space and time. And so that we discussed like a virtual memory systems, how operating system layout virtual memory. And so for that, therefore, for important functionality of virtual memory is, each process has own virtual address space and address need to be translated, and we have to support, layer geolocation. We learn the layer geolocation where applications are loading on demand. Okay, and so that's lead to this picture where address the processes has own address space and they need to be translated into physical memory. This is kind of focus of today's lecture, talking about this address translation mechanism. Then we also talk about these issues of the APIs. So APIs having 2 different layer. one layer is libc layer, the other layer is system call layer, where or libc make a system call to get the memory from the operating system, brk, sbrk, and map. So we discussed several different APIs for libc layer and map system call layer, which is like brk and sbrk. And again, the important API we need to know is mmap. So mmap provides uniformity. So different type of backing storage. For example, file, device memory, shared memory, or non-backing device, which is called anonymous mapping. So mmap providing uniform interface to use this different type of memory. So I actually kind of explained that mmap meaning of map anonymous and giving the file descriptor where you put the file back to memory, etc. Okay, so that is beauty of uniformity in memory mapping using single API, which is mmap. Okay, and one important classification of memory, physical memory, is that one type of physical memory is backed by a file. The other type of physical memory is anonymous memory. So when page fault happens, operating system loading data from the file, which is a file back to memory. In case of file back to memory, when page fault happens, operating system read data from the file and fill the contents in the file. But in contrast, in anonymous mapping, when page fault happens, operating system allocate memory, but initially it zeroes out, give it to application. So what is two type of popular, most widely used in anonymous memory? What are in address space? What two regions are use the anonymous mapping? In processes address space, which region? What region actually used for anonymous memory in process address space? In process address space, what region? What region is used for anonymous memory in process address space? Two, heap and stack. Okay, and file, the text region and data region is file backed because the original binary has the content of code section and data section. Okay, that is the anonymous memory mapping. And also, mapping can be separated as two parts: shared mapping and private mapping. So when shared mapping, one memory region is changed, the changes are immediately visible to other applications' memory. By using this type of operating system, make this created shared mapping. So different virtual address space having identical physical memory. Under the hood, the sharing happens in the cache coherence protocol. I explained that. Private mapping is that is copy and write. So when modification happens, then that modification private to process. So to implement private mapping, the copy and write mechanism is important and key. So we didn't discuss how to implement copy and write. We will discuss later after learning paging mechanism. Okay, so that was the recap of virtual address space, and today we're gonna talk about address translation. Okay, so let's begin. Again, the address translation. So virtual memory design, virtual memory API, and address translation, paging, and physical memory and VM functionality. So we are in the address translation. So again, the address translation mechanism using this using this design. So this address space has to be mapped, and in virtual address space there is no address translation mechanism. So we are three mechanisms: more fixed and base and bound and segmentation. These are three mechanisms we will discuss today. And next time, I think, when is next time? next to Wednesday. Next Wednesday, we'll be talking about pacing. Okay, pacing and copyright and sharing, etc. We will learn the paging mechanism, but this is today's focus. So let's take a look at. Okay, so this address space and this address space are translated. So we learn this important design is called level of indirection. One domain of address space are translated into other domain using some function. So we learn how to implement that function in computer system. Okay. So address translation is like, starting with some kind of application. The application's virtual address space layout is like this one, right? Application code and data here, and heap grows and stack grows downside. Okay, so this is a virtual address space. Initially, let's assume that the executing this code basis. Okay, so initially EBX register contains the address of this 15 kilobyte address. This is address, okay? Okay, so can you interpret this, assembly instruction? What is the, meaning of this parenthesis in register? You learned this in the systems program. What is the meaning? What is the meaning of parenthesis here? Okay, dereference. Okay. Of register EBX, which is 15 kilobyte. Therefore, and moving this dereference data to EAX. So what is the value of EAX? What is the value of EAX? Here, 300. Okay, 300. Okay, so 300. Then learning EAX and adding constant value 3. Okay, so EAX and store it EAX. So EAX going to 3. Okay. Oh, 0x. Sorry. So sorry. This is decimal. This is 0x. May confusing, but anyway. So some value. Okay, and moving, saving this data to EBX. So this one goes to 303. Simple program. Okay. So for this one, architecture fetch instruction and execute instruction, loading the address from the 15 kilobytes, so 300, 3000 are loading into the value of 3000 or loading into EAX, and again fetching this address space and execute this instruction. Okay, and then fetching this next instruction and executing the store to address of value 3003. That is kind of your program. When your program started, your program has starting address of 0 and somewhere. Your binary, your virtual address space always start with 0. That leads to problem of this relocation. Okay. Relocation. So binary data, binary program are loading into address space. Okay, so in address space, virtual address space started with 0, which has to be located in the physical memory somewhere. Let's say this region. But this physical memory started with 32 kilobytes. So here 0 base origin of 0 has to be modified to 32 in physical memory, which process is called relocation. relocation process. So address translation mechanism is about how to relocate this. So application program virtual address space is 0 and physical address is 32. So what is the function that translates 0 to 32 kilobyte? So why relocation is complicated? Why relocation process is complicated? Looking at this example, what kind of thing you have to do? Or loading. What kind of stuff you should do? So in EBX, address is 15 kilobyte. Okay, so if application relocated, if EBX is still 15 kilobyte or not? No, right? Definitely. This address, this EBX origin address has to be changed. So what's the idea? First one is static relocation. Do it. Software-based relocation. Operating system patch rewrites its program before loading it to memory. Okay, that require changing the base address of static data and functions. So for example, this is a kind of function, start address of 0, and let's say I want to move this address to EAX and add evolve and moving to this address space. If it rewrite, then this base is this one, so patched. Patched. And also patched this one. Like this. That is called static relocation. It works, but patching every instruction is very complicated. So static relocation, good benefit of static relocation is no hardware supported. There's no external hardware support required, but it's complicated. So first one, protection is not enforced. So the application is loaded as it is. This application loading it, but there's no protection in software. Clearly. And second problem, after being placed at first, it cannot move the address space. Okay. However, at some point, application's memory has to move around. So we will learn later, which is called external fragmentation. So we need to reallocate process and moving process memory for eliminating external fragmentation. We'll learn later, but this movement is required. But this static allocation is very complicated because operating system only involve the first and loading it. So therefore, no movement after loading it. It is possible to operating system patch every time it moves, but static allocation only support loading time, read writes, and after moving, there's no operating system involved. So movement is is not considered. That's also a bummer. Critical problem is no protection and complicated and movement. So obviously, what is next step we should talk about? With hardware support. Okay, question. At slide 5, figure describe at slide 5. The right figure describes physical address space. Yes, this is a virtual address space. This is physical. Yes. For static relocation, how do operating system know address needs to be relocated and data must be relocated? Okay, so here is still. When operating system loading into physical memory, loading application to physical memory, it knows that this starting address is changed. So operating system looking at every instruction and patch it in the static allocation. very earlier times, operating system did it without hardware support. How do operating system know what address space need to be located? Because this instruction is address. So it analyzes that this instruction is constant or address and patch it. So for more information, we need to looking at some binary where the symbol tables and relocation address space. But let's not get into the binary analysis detail. But for now, operating system has a way to know this some symbol is address and operating system patch it. Just for now. For more details about this patching, you need to learn some binary analysis course. So let's not get into that. Okay, any other questions? Serial location? All right, so the next thing is hardware-based relocation using memory management unit, which performs address translation of every memory reference instruction. So operating system does not patch it, but when applications start access memory, hardware patches it. Hardware translate it. Okay, so again, this protection is enforced by hardware if address space not valid, based on exception, some kind of different exception. Base and boundary, also segmentation, paging, having some kind of exception. Operating system just pass about what valid address space of current processor menu. Operating system providing information about this mapping. So we looking at these three: base and bound, segmentation, paging, implementation. Let's take a look at the first one. Before looking at this, so far we're talking about this kind of a difference, base and bound and other stuff. But here are important design points we need to consider. First, we have to think about how to support memory protection. The protection is key. So when I explain some kind of translation mechanism, think about protection mechanism. Second, how easy to implement this idea? What kind of extra hardware support required? A second design point. Consider. Third is the most important: fragmentation, memory, space efficiency. And third, in case of sharing, what is basic unit for sharing? So sharing granularity. Third, we're not talking about this time, but after learning page, how to support this lazy on-demand allocation. Also 3 points. So for base and bound, segmentation, and this fixed allocation, it doesn't support on-demand allocation. So it's not in the context, but after running the paging, we're talking about this on-demand allocation. Okay, so let's talking about this issue. So fragmentation has two different meanings: internal fragmentation, external fragmentation. So I will explain first. Let's say this is a unit of D. This is memory. I allocate this amount of chunk. This amount of chunk. Let's say this memory location. This is let's say this is a 16 kilobyte. This is a 4 kilobyte. This is let's say 8 kilobyte, and this is not free, not used, free. Let's say this is a 16 for 12 kilobyte, free and used. However, in some application, even if operating system giving 16 kilobyte, only using this one is actually used. This one is wasted. What I'm talking about? Am I talking about internal fragmentation or external fragmentation? It's wasted. So this one is not utilized. Space is inefficiently used because allocation is given to 16 kilobyte, but application only using 12 kilobyte. You see internal external. What I'm talking about, internal, external, okay? Internal. So what actually kind of affect degree of internal fragmentation? What effect? So why this kind of problem happens? Why? Fundamental. In memory allocation perspective, why internal fragmentation happens? Why does internal fragmentation happen? What is has to do with it? Okay. Not on demand or assignment or location size. If allocation size is big, for example, 16 is minimum allocation size, then application only using 12 kilobyte, 4 kilobyte is wasted. If application operating system decrease allocation size 12 kilobyte, application use 12 kilobyte, nothing happened. If operating system increase basic allocation size to 20 kilobyte, internal fragmentation get more severe by 8 kilobyte. So internal fragmentation has to do with allocation size. Okay, so that's kind of observation. Second, I want to allocate 16 kilobyte contiguous memory because this memory is contiguous. But so totally it has 4 kilobyte, 16 kilobyte, but cannot find 16 contiguous memory does not exist. This problem, what I'm talking about, internal, external. Internal, external. This is called external fragmentation. Okay, so I described the internal fragmentation closely has to do with allocation size. External fragmentation is that the amount of memory, total amount of free memory, the available space is 16, but because they are not contiguous, they cannot allocate more. So operating system cannot allocate memory, which is external fragmentation. So again, what is fundamental reason that what kind of affects this external fragmentation? What aspect? So internal fragmentation, allocation size. What is kind of fundamental reason that this external fragmentation happen? What is key factor? Size, free, no. Offset, allocation, okay. Placement. How the physical memory are placed affects external fragmentation. So, meaning that better placement strategy, giving some less external fragmentation. For example, this memory, I'm moving into upward, and if there is a free contiguous chunk, external fragmentation is gone. So how to place used memory affect external fragmentation, how much allocate at one time affect internal fragmentation in general. And internal fragmentation happens if allocation is smaller than program size and thus divides to program size. Okay. Can internal fragmentation happen if allocation is smaller than program size? And does it divide it to let me see, program size? Does not divide it to program size. So allocation size by program size 15. In case of programs, so one question from the one student. Let's say application using application program using 12 kilobyte, but memory only has memory only has 5 kilobytes, for example, say. In that case, internal fragmentation happens or not? How do you think? Is it a question, right? Is it your question? Correct? Oh, is it? Yeah, I think a program. I think the memory should allocate 15 kilobyte. Let me see. I think memory should allocate. So in term, memory should allocate 15 kilobyte. Oh, I see. Okay, good point. So I see. So let's say basic unit is 5 kilobyte and program only is 12 kilobyte. So how to do that? Application using operating system has 3 chunk of 4 kilobyte, right? So 4 kilobyte, 4 kilobyte, 4 kilobyte. Application only using 12 kilobyte. This one is wasted. So in this case, is it still internal fragmentation happens or not? What do you think? Yes or no? Click if you think this is also having an internal fragmentation. Click yes. If you think this is not internal fragmentation, click no. Answer. This case. This also happens. Internal fragmentation. Due to this 5 kilobyte unit, 3 kilobyte chunk is wasted. For example, if memory allocation is 1 kilobyte, moving to 1 kilobyte, every memory allocation, which means that you only allocate 12 chunk, then fine, no internal fragmentation happens. So if you do this, in that case, if your allocation size is smaller, then no internal fragmentation happens. We will learn this one, the pacing, later. But what? So then, problem solved. Making the memory allocation size smaller and smaller, then no internal fragmentation happens. But why memory management system experience, even if there is some kind of internal fragmentation happen, operating system and many memory management system having some kind of minimum granularity of allocation. Why? What is problem? Maintaining 1 kilobyte is too expensive, so inefficiency. So we will discuss this topic in the pacing later. So even in the pacing, the overhead is too high, so there's a trade-off. So people conclude that later 4 kilobyte is kind of reasonable size. That's empirical. It's not kind of final scientific. So people looking at the application, 4 kilobyte is reasonable number. So 2 to the 10 is reasonable. So people choose it. Right? So that's all answer for internal fragmentation. Okay. So distinguish case where internal fragmentation and external fragmentation. We'll discuss different mechanisms and looking at discuss benefits in terms of internal fragmentation and external fragmentation. Okay, that's key evaluation and design points. Right. So let's start with very basics. Most simple, clear mechanism, hardware supported mechanism. So applications virtual address space is there, and hardware having a new hardware. Base register and adder. So fixed partition is the way that physical memories are broken up to a fixed, defined, fixed partition. So each partition is the same and fixed. So number of partition and degree of multi-program. So each program having loaded in 2 different partitions. So process 1 use partition, process 2 use this partition, process 3 use partition. So if process has its own virtual address space, the virtual address space are translated into hardware by adding this base register. For example, if partition 0 used, the base register is 1000. If partition 1 used, then base register are 2000. So added. So this is physical address space. Simple and working mechanism. what is problem of this fixed partition? What do you think? Oh, first of all, this 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 fixed partition. Okay, so clearly the first one is the hardware requirement is just base register and the adder. So very simple, very easy to implement. Second, let's think about the context switch. What do context switch? If your application changes, or simply hardware changing the base register value for context switch. Super simple context switch. Context switch has to do with the hardware state that needs to be changed over processes and operating system. But unused area in a partition erased. Internal, external, external, again, internal frame. Why? Because allocation unit, internal fragmentation is all, has to do with allocation unit. Allocation unit is always fixed, so internal fragmentation is severe. So partition size, one size does not fit all the program requirements. Does not support protection. So this fixed partition protect. How does it? Does it provide protection? How does it how application? So protection, yes. How does it protect? Because this size is fixed. Size is fixed. Okay. So if application trying to access the address space beyond the size, for example, having a pointer that beyond the fixed size, hardware can reject it. So, for example, in application, so this because of this partition size is fixed. If it's go beyond the size, then kill. So this fixed partition is more, the protection is will be more elaborated later for this protection. But this protection is only access or not. More fine-grained protection, for example, permissions and read-write permissions, that is not applied in the fixed partition, but only for when application in trying to access the other partition, because size are fixed. If you go beyond boundary, hardware kills it. So that's the simple protection mechanism provided in fixed partition. So the key problem of this fixed partition is internal fragmentation, because due to the fixed size. So later, to solve this problem, to improve this fixed partition, hardware designer and bring up new design. How to solve this kind of fundamental problem of fixed partition? How to modify the length? How to solve this fixed? By giving length, which is called base and bound. So two registers are introduced. One is size, the other one is base. So in virtual address space, base and bound. So actually the fixed partition also having this have this bound register, but fixed. But in case of bound register, hardware first checks whether this virtual address space go beyond bound size. virtual address always start with the length of 0. So if this virtual address length is beyond the size, then protection fault happen. If not, then go. Okay, then this base register adding to this length 302 and going to this partition address space. Because of this bound register, each partition application has variable length, variable sized partition. Okay, so that is basic base and bound. Obviously, using the base and bound, application running in this virtual address space here and bound register 16 kilobyte and base register 2 kilobyte. That is relocated into applications physical memory address space. So okay, in the first example, when EBX register here, let's say 16 kilobyte, so say 14 kilobyte address space are translated into somewhere here. What? 14 address space, how to translate it to 14 in address space in base and bound register cases? Simply 42. Hardware translates 32 kilobyte, 14 kilobyte to 46 kilobyte by hardware. So automatically hardware translated and use this address space for physical memory space bound. Simple design. Okay, so that adds one more register, bound register. Okay, so again, the role of bound register is what? What is the basic rule? Protection. Okay, variable length protection. Okay, pros. Simple, still very kind of inexpensive explanation compared to later mechanisms, so earlier pages, and less fragmentation than fixed partition. What? Less what? Internal. Does this mechanism eliminate fragmentation, internal fragmentation? Completely eliminate no internal fragmentation? No. Internal fragmentation still happens, but much less. So theoretically, to eliminate internal fragmentation, what should be the allocation size unit? I mean, no internal fragmentation, meaning that theoretically, what is the allocation size? 1 byte. Okay, so every memory allocation having some kind of granularity, having problem of internal fragmentation, but degree is different. Okay, one byte. 1 byte is kind of identical unit, but that's not practical. Okay, so that's less internal fragmentation than fixed partition. Cons. Each process must be allocated contiguously in physical memory, like a fixed partition. That leads to this problem. Some holes are scattered around in the physical memory. So to reduce this internal fragmentation, some kind of mechanism compaction, I'll talk about later, compaction is required. So what fragmentation I'm talking about? External. Okay, now, fixed partition, does it cause fixed partition? Does it cause external? Does it cause external fragmentation problem? No. Why? Because every memory is, statically same size partitions. So no external fragmentation happen. Fixed partition problem. That's very important observation for pacing. Pacing having some kind of better way for modifying the fixed partition. But let's talk about later. Okay, fixed partition. But what But if external fragmentation doesn't happen in the fixed partition, why don't we use the fixed partition instead of the base and bound? Why still base and bound is preferable, even if fixed partition doesn't have internal fragmentation? Why? Why? What do you think? Yeah. Okay. So because internal fragmentation is 2 CPU. Okay. So if total sum of waste memory, base and bound has memory is wasted due to the internal fragmentation and fixed external fragmentation, and fixed partition wasted memory by internal fragmentation. But in general, fixed partition wastes more memory because of the internal fragmentation of fixed partition is severe. That is the reason. So base and bound has two problems. Still has internal fragmentation, external fragmentation, but total sum of waste memory is less than fixed partition. So use it. Now let's talk about sharing, partial sharing. For sharing address space, two virtual address space has to map the same physical memory. But in case of base bound, there's no partial sharing. Entire base and bound. So base and bound. This is a base and bound of process one. So process one used by this entire base and the memory region to specify the base and bound. This entire physical memory in itself has to be shared in its entirety or not. So sharing granularity is entire reason for base and bound specified. So no partial sharing is supported. The question from question: if external fragmentation can still happens in the fixed part, external fragmentation can still happen in fixed partition even if free memory of contiguous chunk. Okay, so here, a good question. Okay, so let's talk about that. One more clarification. Let's say this is a location. Partition one, partition two. So your application free some part of that. Then this part of the memory can freed or not. In fixed partition or base and bound. Application free heap, some part of the free heap. Then this memory region or some this part are freed in physical memory or not? No. Okay. So freeing some kind of internal freeing the objects of a process cause external fragmentation, internal fragmentation. What happened? What caused? Internal fragmentation. Internal fragmentation. Okay. So does it answer for your question, Tang-Nung? So you are talking about internal fragmentation right now. Application only exit, then entire partition is gone. So no, and then same partition is allocated, so external fragmentation doesn't happen in fixed partition mechanism. Oh, process exit safe. Here still, same thing. If process exit, I always allocate fixed chunk. So process exit and this chunk is gone. When process comes, this free chunk can use it. So there is no external fragmentation. Same size. If physical memory are managed by same size, there is no external fragmentation. Can one process get? Oh, okay. Question: can one process get two and more chunk in fixed partition? No. One process use only one chunk. Each process is only assigned with one chunk. Yes. One process use one chunk. Base and bound same. One process use only one base and bound chunk. What program size? If program size is larger than partition size, we cannot loading the program. So in that case, program is never loaded. So you have to or set the operating system to increase larger fixed size chunk. So in that case, not loaded. So that's invariant. Program size always should be less than fixed size chunk. Any other questions? So this is kind of not super duper, fancy systems, the earlier days idea. How difference, if program size is larger than partition size, how is different from the external fragmentation? Okay, in case of this the fixed size chunk, no, if program is larger than one chunk, cannot load it. So you have to increasing the one side chunk to bigger than the program size. Okay, so that is basic, you have to think about that way. And how to determine the value in the bound register? That's a good question. Good. So base and bound register size is here still. So that is related to question. So here, application, and if program use it, so this is the base and bound. If application trying to use more memory, then exception happens. Then OS increase bounds register size. That was the basic concept of the base and bound. So I'm not talking about this is demand allocation. So I want to talk about demand allocation later in later section, but base and bound also today. If there's no allocation happens in the business, then your program killed. Cannot use more memory, so out of memory, your application killed. If the other application is still using here, then killed. Very naive implementation. Any other questions? Okay, so base and bound specify, again, don't get confused that base and bound specify the one reason, and here entire application code heap stack should be allocated. Does the no partial sharing only occurred in the base and bound mechanisms? Okay, so partial sharing mechanism, we will revisit the concept in later section, later mechanism. So get back, let's talk about later. So, any other questions about base and bound? All right. So, so we're talking about fixed and make the physical memory mapping for variable size using by adding new bound register, but still it has this internal this internal fragmentation and no code sharing. So the idea of next mechanism is using this one. Oh, sorry for that. Before explaining the next mechanism, let's take a look at some kind of operating system issues I want to explain. So using this base and bound register, so operating system has to design first how to start process, and when process is terminated, when context switch happens. So this is kind of kidding. For base and bound, operating system has to maintain the free contiguous chunk. Okay, first, when to allocate some process, let's say the process use some basic size of the base and bound register, and finding contiguous chunk first. That's the first thing. So if it's allocated and operating system use it. When process is terminated, for example, process use this chunk 32, then operating system has to add this free chunk, this part, to put back into free list. So free list chunk is also one thing. And then when context switch happens, basically operating system has to maintain this base and bound register where in process control block. So process control block has to save this two register value, base and bound. And when context switch happens, the base and bound register values are changed to different process. Simply. So this is what context switching happens. Again, fixed partition, there's no bound, and base and bound to register. Question: shouldn't it also merge chunk? This one? Talking about, yes, it can be merged, but for simplicity, I just kind of show that in a free list. It can be merged. Later in body system, the free chunk, this contiguous chunk can be merged, but for showing some kind of simple free cases, I just kind of made it. But it can be merged in the modern operating system. Okay. So okay. The next design is improving the base and bound. Base and bound, it has internal fragmentation. Okay. So when big chunk, so in the big chunk, application can using stack and heap and code. And there's some place in the middle is free. But despite of that, in base and bound pace, OS has to allocate big chunk that cause severe internal fragmentation. First problem. Second problem, again, this external fragmentation in base and bound, and no partial sharing. So let's focus on the first problem. To reduce this problem, application having this section, heap and code and stack, but despite of these different things, this grows, grows on demand. OS has to be one big chunk that causing severe internal fragmentation. How to reduce this internal fragmentation? What's the idea? Thus, bound size increases with the fixed amount of Changyan, I will get back to your question after discussing this one. So, what is the idea of to improving this base and bound implementation? How to do that? Application having a different chunk, different memory region? Impossible? So how to do that? Is it impossible to? Relocation? No. What to do? It's possible. I mean, it cannot eliminate internal fragmentation, but reduce internal fragmentation. By what? Changing position of heap. Exactly. So let's say base and bound for code, base and bound heap, base and bound for stack independently, which leading to segmentation. Okay. Segmentation is divide address space into logical segments, where each segment corresponds to logical entry in each address space, code, data, stack, and heap. And this one, so this using segmentation, operating system view this memory as collection of base and bound business. Okay, and each segments are managed independently. Okay, so base and bound, so natural extension of variable partition. So base and bound, only single segment per process. In segmentation, many segments, code usually typically four segments for each process. That leading to eliminating this internal fragmentation, because it cannot eliminate internal fragmentation like this free. So there was a question. Does bound size increase with the fixed amount of size? No, it depends on. So for example, how to increase bound size, it depending on some operating systems implementation. So base and bound only specify the size in hardware. So how to increasing the bound register size is completely operating system detail. But usually it increasing fixed size. For example, not like some small size, but some kind of granularity. But that's not what is the kind of best value. is not specified in the hardware. Okay, so that's operating system implementation specific. Second question, when scheduling process, the process should be always located in the same location. I mean, process are their unique base, right? No, where application actually process is executed and loading into address space, operating system find the free space, which means that the physical memory of process can be changed over, any time when process is loaded. Does it make sense? Okay, so right, so that leading to segmentation. So Seung-jun's actually question, yes. For that part, for supporting these 4 different segments, definitely more hardware cost, more register, base and bound register are required at the cost of this granular, or at the cost of this segmentation. So let's take a look at the idea: fixed, base and bound, segmentation. As this mapping mechanism evolves, what does it mean? What is the key factor that the direction of evolvement? What are key factors? Okay, reduce the fragmentation by what? How? Fine-grained mapping. Making the mapping granularity more fine-grained to reduce the internal fragmentation. Therefore, what are the next direction? And just kind of before talking about the thing, what is the next direction after segmentation? What should I talk about? One of the most fine-grained mapping, phasing. Same thing. Okay, so that is the direction of the mapping mechanisms. So we are talking about segmentation and then moving to phasing. So that's key, moving momentum, making the fine-grained mapping, so reducing the internal fragmentation with small cost of hardware. Going this one, hardware cost decrease, obviously. The number of the hardware to support this mapping and some context switch costing increase. At the cost of fine-grained mapping, hardware costs get increased. This is kind of one trend. Segmentation. Let's take a look at segmentation. There is an implicit approach and explicit approach, but that's most hardware supporting this explicit approach. So it means they use a part of the virtual address space as segment number. All right. So I say that for segment, code, data, heap, stack. 4 segments exist. So how many bits? 2 bits. So in some operating system, you share code, data, heap, depending on segmentation system. Some system having a shared code, data, heap. So here still some systems having kind of, how can I say? Oh, sorry. Heap is growing. So let me see. So this is kind of one segment, and heap growing, segment get increased. So one segment assigned for code data and heap, and stack is keep increasing. So one segment per stack. So that is kind of one example in the figure. So 0, 0 indicate then user code, data, heap. Some operating system use different way. So only 4 segments possible. So some operating system using code for 1 segment, data for 1 segment, heap for 1 segment, depending on. But this example is this case. Okay, and using different segments per stack, and this is for system. Why this scheme makes sense? So segment is given to operating system, and operating system use this segment for different purposes. Why separation this and this system? For what? Why separate these two segments for user cases and system segments? Why? Kernel data. So the system used by kernel in case of this example, and this stack and heap used by a user process. By separating segment, this kernel segment can be protected from the user segment. For that purpose, this segment scheme, this example, use it. If some operating system does not need to protect kernel from application, then use code and data heap for different segments. So that's kind of one example, right? So anyway, so these 2 bits used for segment indicator. So using the segment indicator, segment has in this one, code, data, heap, stack. So I want to kind of sorry for the computing case, but in this case, segment, this bit used for code 00. This 01 is data, 10 is heap, 11 is stack. This is code, data, this is heap, this is stack. So hardware translate this one as the first segment, and operating system use this part as code, and which has base and bound. Okay, for now, let's focus on this one. Okay, grow, protection, validity, explain later. Okay, and so in case of this one, let's say 01 indicates first segment. So it using the base register of this one and bound register this one. So this address is translated to this one. What is translation of this one? So what is outcome of translation? Yes. So this number is smaller than this one, so it's not violate protection, does not cause exception. So number is, what's number? Translation number. This one. So goes to this segment. Again, if this virtual address beyond the size of bound, it causes segmentation fault. Okay, so that's one thing. The second thing, there's a protection. So this segment has read only and and heap and stack and data is read write-up. There's some protection. Valid is operating system stated. So without validation, at first time, when validation is 0, the operating system accept segmentation violation happen, operating system fit it. So let's not talk about validity. Grow, again, stack grows backward, and which means that extra hardware support for needed for growing direction when translating. So code and data and stack grows downside and stack grows upside, so it has growing direction number here. So segmentation, this is what is called segmentation table. Set of segmentation table consists of base and bound, base register, bound register, growing, and some protection bit and validity. So that is extra hardware require for protection or for segmentation. So the segmentation is translation by this on this way. Okay, so segmentation, any questions of segmentation? It's clear, right? So it's kind of, translation mechanism is the same as base and bound, right? And for supporting, segmentation can share between what? Segmentation unit. So for example, code sharing is still required today. For example, I want to sharing the code, but the segmentation is basic granularity of sharing is each segment, each base and bound register shared. But for sharing, it's important that this shared segment must having an identical page protection. For example, I want to use this memory for read write. I want to use this memory for read only. Then these two segments cannot be shared. So to share process can pointing to same segments, but this segment and this segment having the same protection. Protection is not identical, operating system cannot share. So this is kind of why the segmentation required for protection bit. Sharing, protection bit has to be added to to having a same kind of same protection mechanism. That's one thing for segmentation. So that leads to kind of a very simple discussions of segmentation. So it kind of much sparse allocation for address space. What I'm saying is that stack segment and heap segment can be separated and grow independently. Okay, and it much easy to kind of protect segment. For example, I want to kind of turn off the valid bit, then that segment access can causing segmentation fault. And also this protection is made by this bound register size. And also using the segment, we can separate kernel mode segment and user level segment. I giving the example. Okay, and sharing is much better than base and bound because I want kind of in case of the segmentation granularity much smaller than original base and bound case. Okay, and also the dynamic relocation for each segment. So so compared to base and bound, oops. So compared to a basic branch and bound, it supports dynamic relocation of each segment, meaning that each segment has to be relocated in the physical memory in its segment granularity. So it's much more flexibility for managing physical memory space. That actually helps to eliminate external fragmentation. So for external segmentation, I need to talk about some, memory compaction mechanism, but because of time limit, I need to stop, and then we will rediscuss pros and cons of segments and moving to paging lecture. I need to plan to this segmentation, but I need to stop here. All right. So okay, there are some several questions for segment, but before that, I want kind of announce Pintos quiz. First, Pintos quiz, and let's get back to your question. Pintos quiz first, offline. So we actually reserved the the offline room for all students, and the room time will be the Monday 1 p.m. and the place will be announced. Place will be announced in Piazza. So please keep it posted. So information will be posted in Piazza. Second, you will use bring your laptop. So what we want to do is that we will use safe browser. That browser only can navigate specific website. While browser is turning on, you cannot, use other programs. It's kind of big model browser, and you cannot using the KakaoTalk and any other messengers while browser is only on. That browser leading to our GitHub website of Pintos. So all the Pintos answer the patch of the the solution, all the full blown Pintos code will be given, and then you can navigate it using the GitHub. So and via safe browser. Then we'll prepare two to four questions depending on the difficulty. So the reason is that if you give many times, long times, for 2 hours, you can actually understand source code in the place. So to avoid this problem, we will make the time short relatively. So if you already studied, you can easily answer the questions. But if you do not, then we don't have much time. We are not much give time to understand code at this spot. So 2-4 questions and the time, we are actually kind of selecting the problem right now. So depending on how many problems actually we select, we will announce the time. That was the quick question. Any other questions about it? Does it work macOS 2? Yes. Windows, macOS browser work well. We already tested in the when in the the Corona area. I will give online exam. We will already test it. We'll work in the Linux. I will check it. Linux, check it. Good. I think it works, but I'm not sure it works in the Linux. I will double check. Other question. Okay. Is there an outlet to charge the laptop? No. So please bring. So no laptop charger will given. So if your laptop is out of power, that's kind of your thing. So in that case, it's kind of nightmare. So we cannot prepare laptop charger in the room. So we are supposed to write in code, but explain conceptual. No, we are not. The question is about understanding. So we're not writing some programming quiz. You can look at and understand code. There are several types, but I don't want to give you some specific type exam questions because you are very fixed. So do some various tests. Will we request the code? Will we be requested to code the same lines? Some line? No. The code writing is not. Will the exam question we provide? No, I will not. Otherwise, you very fixed. So I will not give you some kind of specific exam question. Are we supposed to write in code for explain? Okay, and will the question will provide? No. And do you recommend focusing on big picture or line by line? Also, does so for part of okay. So looking at some questions, I actually mixed that. Some questions are related some understand big picture. Some questions understand some important line. So why this lacking? Yeah. So focus no, and both are actually the exam, the Quintos quiz actually asking the both part, some kind of big picture and some kind of small aspect of how the code are executed. Both have been. They are handwritten? Is that plug or for? Are they handwritten or is that plug for charging? For answer, we prepare some offline sheet, but mostly you will do online, typing stuff. If it's problem, we prepare offline, paper in case of your laptop is gone. But by default, you will type in online because that's much easier to grade and manage. So for charging problem, I'll think about the TA, but you should be fully charged before going to exam. Does it mean two, three mean given for each problem? No. It's not. Two and four questions. Questions. Two will be hard. Four is relatively easy. So there are hard questions, easy questions. So I'm just kind of looking at. Any other questions? So all these details will be posted in the Piazza. Can I use Korean answer? Yes, I will allow to use the Korean answer. Are we allowed to keep out GitHub viewer? Can use it? Can we use any editor? Only viewer. So you can only viewers and look at navigate the GitHub code. Solution is provided. Yes, we provide the code that solution patched. No, I don't think. GitHub has some way to navigate it, so you have to use it. So it's not kind of VS style thing. Sorry. But if you look at the GitHub and then symbol searching, it works. Those quiz cannot use any GDB run. No, you cannot run. If you're allowed to, the reason that we are using the GitHub source code, if you run it, you can easily understand how does it work. So we are not allowed to run the program in the queues. My laptop monitor is broken. So is it possible to isn't that so? Yeah, yes. Okay. If you have any problems bringing your laptop, please contact us. I think we need to prepare some mechanism for some way to, rent the laptop. But yes, if it wouldn't support, can I use VMs? I will talk about this Linux issues to TAs. I will double check. I'm operating a specific part of the GitHub code. Do we need to log in? And am I correct? Can I log in the safe browser? Can we log in? I'm operating to search a specific part of the GitHub code. Oh, okay. The safe browser specified only specific URL. If you kind of access different URL other than specified, you cannot. So don't worry about that. You cannot navigate any code in the GitHub, only specified URL. And that URL is our, CentOS GitHub repository. Don't worry about that. Okay, that was the kind of, quiz, and quiz time will not be long, so it will be short in the middle. Is there any list of websites, accessible us to view? So for that thing, yeah, we will kind of announce our GitHub pages. You can navigate it. So okay, so good point. So I'll talk to TA that what kind of source code you can navigate it in the Pinterest quiz. So I will kind of open it this week. Okay, so we can actually do a practice to how to navigate source code in there. Okay, so I will let you know. Okay. Any other concerns? Sorry, I know. Because of the long time, I think students has to leave. But for more details, I will post it to Piazza. Okay. So that's all for today. And there are some questions about the Windows contents. No, the segmentation contents. I will ask your questions. But other than that, please feel free to ask it your Piazza. Okay. Is the total time? What is total time? I'm kind of considering. So it's just 2 weeks left. So we are kind of picking questions, and total time is not yet decided. So I will post it. But for now, I'm not sure. But total time is less than, I think it's not more than 1 hour. All right. Okay. So thank you, and talk to you next Wednesday.